Okay, so this question came up before, and I'm just going to do a proper solution to this. So it's to show that the area of an ellipse is equal to this area. So the area is pi times a times b, and we're given the equation of an ellipse here. So if you've met trig subintegrals before, this is actually really it actually utilizes trig sub stuff fairly well, and it teaches you kind of a lot about general integration techniques. So let me just get my notes here because I did it before. I don't want to make any mistakes. So this is indeed the general equation of an ellipse. Although you can't necessarily find the perimeter in a very nice way, you can find the area given by pi ab. You can see it's dimensionally correct because both a and b are actually lengths. They're the corresponding major and minor axes of the ellipse. So the first thing I'm going to do is I'm just going to draw a sketch of a sample ellipse that we might have. Now, my circle drawing is not great, so my ellipse drawing is not going to be great either, but there's my ellipse. It's also very rotated. We can have this rotated as well. So there's our ellipse. How I'm going to do it is I'm going to actually integrate the area between these 2 points here, so forming this pink area here. Then I'm going to times it by 2 because an ellipse is obviously symmetrical about itself, or at least about the x-axis. So actually, how do we get the x-coordinate of these points? Well, we can see that clearly it's on the x-axis, so the y value has to be 0. So if I call these points x1 and x2, I'll say we can say xn, so any or either of the x's, is found when y is 0. So we can get x over a squared plus 0, so it's going to be plus 0 and then equals to 1. Then just be careful when you're taking square roots, that's actually going to be plus or minus 1. So that implies that the x coordinates are going to be plus or minus a. So clearly we're going to have a plus a over this side and a minus a over this side. Okay, cool. We found where we're going to integrate between. So now we're actually going to integrate our function. And we want y as some form of f of x, which can then mean in sort of very hand-wavy terms, we get the integral of y dx equals the integral of f of x dx, where clearly this y dx term is just going to represent our area, which will represent by capital A. So where do we go from here? Well, I'm just going to rewrite down the equation again. Just if I scroll down a bit slightly. X over a squared plus y divided by b squared equals 1. Now I want to get this into a form where it's just y equals, so I'm going to do y over b squared is 1 minus, and I'll just write it as x squared over a squared. Then how I'm going to actually write this is I'll just take the square root, but I'll just keep it as y over b, just for now, as the square root of 1 minus x squared divided by a squared. Now, this b, it doesn't necessarily matter where it goes. It can go on either side. Sometimes I actually leave it in the denominator, but this time I'm going to just multiply it across. So b root 1 minus x squared over a squared. Now, the reason this is positive, we took a plus minus before, because in fact the x values can vary on their axis. But in fact, the y values we've said are strictly greater than 0. That's how we're going to approach this. So that we know that y is greater than 0, so therefore f of x is also strictly greater than 0. Because of this domain in here. We're assuming as well that both a and b are actually positive constants. I should have actually specified that before, but there's just a proof of motivation that it's not going to sort of flip any signs, it's going to keep both terms positive. So now we're just going to integrate both sides. I'm going to keep the b out the front. Y dx we know is just a, that's fine. Then if you integrate this with dx, we're integrating between minus a and plus a. But how do we do this integral? Well, the first thing we're going to do is, because this looks like a trig subintegral, we're just going to start with that. So normally you do u equals some function of x, but now we're doing x, the thing we're trying to integrate with respect to. We're turning that into some sort of unknown quantity that we're trying to find. And the particular expression we're going to need is actually a times sine of an angle, which I'll just call, I've been calling it theta for a while. Let's call it phi. We'll give phi some love. And when we differentiate that, we get dx equals a cos phi times d phi. Now, I have tried this before without changing the limits at first, because normally I don't, but it's actually a lot easier to change the limits now instead of relying on some inverse sine stuff to sort of carry us forward. So how's this going to work? Well, we know that at x equals a, then we're going to get a equals a sine of phi. So sine of phi therefore has to be 1, which implies that for acute phi, it's going to be positive pi over 2. And at x equal to negative a, we're going to get negative a is again still a sine theta, and then following the same steps, we'll get phi is actually minus pi over 2. So we're changing the a's plus a minus a into actually pi over 2 and minus pi over 2. And this is actually where the pi factor comes in to the pi ab. So again, it's very cyclical trick, but it's all going to come together at the end. So for our area, we can write as b. But now we're actually integrating between minus a and, or minus pi over 2 and plus pi over 2 of square root of 1 minus, now x is a sine phi, so a sine of phi squared divided by a squared times by dx we know is a cos phi d phi. So again, we're still integrating. But now we can do some cancellation. So we can see that there's going to be an a squared popping out here and an a squared popping out there. And so we're actually going to get the square root of 1 minus sine squared phi under the square root. But because we're multiplying by a, I'm actually going to throw the a outside as well. And we'll just be able to times by cos of phi. So let me just rewrite that as cos of phi. Whoops. So cos of phi, still a d phi, because we haven't evaluated yet. So a equals a times b. Still integral minus pi over 2 to pi over 2. It's important that you keep this notation the same. Now, for the thing under the square root, we know that sine squared of phi plus cos squared of phi has to be 1. So 1 minus sine squared will give us cos squared. And again, we're keeping everything strictly positive. So, especially for acute sine and theta, that they're all strictly positive. Is that this becomes a cos squared, root of it is cos, so it actually re-becomes a cos squared of phi, d phi. Now you might have done straight up the integral of cos squared phi d phi before, but if not, I'll go through the process. We actually use one of the double angle formulae, and in this case, cos 2 phi is 2 cos squared phi minus 1. So that implies that we can write cos squared phi as 1/2 of 1 plus cos of 2 phi. So I'm going to include that in here. So AB integral minus pi over 2 to plus pi over 2. Now again, we can factor a half out, and we're just left with 1 plus cos of 2 phi d phi. So we have a is ab over 2. But now I'm actually going to evaluate this integral because it's fairly trivial. We're going to get phi plus 1/2 sine of 2 phi. If that's not clear, then we probably should go back and look at a simple u sub. But also the formulas in the log tables anyway. So that should be okay by this stage. If you're looking at this video, then it should be clear why cos 2 phi integrates to 1/2 sine 2 phi. So now we're evaluating between minus pi over 2 and pi over 2 of this. So when we're actually evaluating, so I don't need actually these eval ones. If you plug in pi over 2 first, we're going to get pi over 2 plus 1/2 sine. Now the 2.5 will cancel, so it's just sine of pi. Take away negative pi over 2 plus 1/2 sine of pi. Sine of minus pi, whoops, because that minus carries over. But if we look actually at the sine graph, sine does become negative at x equal to pi. And then here as well, it becomes it at minus pi. So there's minus pi, and there's pi. That's when they both become negative. Or go from being positive to negative, or negative to positive in the case of minus pi. So in fact, these both go to 0. And all we're left with is an AB over 2. Now, that's going to be plus, or pi over 2 plus pi over 2, that's just pi, which ends up implying that half of our area is AB pi over 2. So what we do is we account for that second area that we didn't consider. So we're going to have 2 times A to get what I call the A true, so the true area. So that implies that our true area of the entire ellipse is this times 2, or pi AB. That's the proof complete.